let's look at the proof of the split vanity address generation. Okay, so here's the basic method that we have. So Bob has a private key and an associated public key. We'll call it A, and big A, little a for the private key, and big A for the public key. He then asks for Trent to create a Bitcoin ID which has a certain text within it. So Trent goes and tries lots of different private keys to then associate them with a public key, and then tries the public key and the private key and the public key of Bob and the new public key together by adding them. So this is an additive function, and then taking a hash of them to produce the Bitcoin address. He keeps trying until he gets an address which actually has the text in it. So he then sends back B, which is the private key he's found, and big B, the public key. Bob then takes his private key and the one that Bob created and creates a new private key. So there is no way that anyone can know what the private key is that Bob has generated. Trent publishes Bob's public key as the hash of the two public keys together added. So in this way, we can actually allow Trent to be able to generate the public key, and for Bob to keep the private key separate. So there's the method, A and A there, B and B. Bob calculates Trent will calculate Bob's public address as the hash of A and B, A plus B, and then Bob's private key will be the additive function of A and B, which is the private keys that Bob and Trent created. The public key will be the hash of the two public keys added. So can we prove that this is actually correct? Well, here's the code that we could prove it. So we'll allow A and B to be generated as random keys. These are scalar values. Then we'll calculate the public key by multiplying A times G, which is the point on the elliptic curve. That will give us 2 points, which are our public key. We then multiply B by G, and that will give us 2 points on the elliptic curve called B. So this will be Trent's public key, and this will be Bob's public key. This will be Bob's secret key, his private key, and this will be Trent's private key. So now what we'll do is we'll calculate a value. So we'll take an addition of A plus B, the two public keys together, and then we'll convert that into a Bitcoin address. On the other side, we'll take the two values A and B and we'll recalculate to find the Bitcoin address. So over here, we take the two keys and we just basically add them together. They are linear values, so we add them together. We then multiply by that value to find the public key. So that's A plus B times G. And then we'll convert that into a Bitcoin address and see what we get. So if it all works, we should be able to prove that this is the same as this. So let's find this. Okay, so the code we're using is this code here. Okay, so we use standard elliptic curve. There's the code. And now what we need to do is to prove that the two public keys will be the same. So we just generate one. There's Bob's private key. Remember, that's a linear value. There's his public key, which is a point on the elliptic curve, which is the G value, the G point, multiplied by A. Trent will pick his private key and then multiply that by G to get this. If we take the two public keys together and add, so we're adding points. So we take one point and then we add the X value and to the other one, and then the Y value too, to get an XY point. We then take the hash of that to find out what the Bitcoin ID is. And we see it's this. And now Bob takes A plus B, and we'll get that. So to be that value plus that value, then calculates the public key, which is two values, and takes a hash again, and we get the same value. So we've actually proven that this actually works. Okay, so Bob can publish the hash of A plus B here, and Trent can publish the hash of A plus B, and over here Bob will be able to calculate the overall private key which is associated with this public key. Okay, so I hope that makes sense. If you want to have a look at the overall presentation, I'll leave the link below. Thanks.